So we stopped at this picture yesterday. So this is what an ideal tetrahedron looks like, with a parameter which is a complex number associated to every edge, and these three and the remaining edges, once you know the parameter for one, you know the parameter for all of the edges. So I am going to denote this as delta z, and z prime is 1 upon 1 minus z, and z double prime is z minus 1 over z. What happens is, if you now take the length of a vertex, which is just, you take a regular neighborhood of a vertex and then just look at the boundary. So there is this length triangle here. If you take this length of a vertex, that's the way we obtained this was to take this triangle and put it at vertices 0, 1, and then this is a complex number in the upper half plane. So this is your imaginary of z greater than 0, and if you are looking at up from the top, this is the edge. This vertex is basically an edge. This is what is z. Then this vertex here is what is z prime, and this vertex here what is z double prime. So this is the way you see it, and moreover, because angles in hyperbolic space are Euclidean angles, you also get that the angle over here, so the angle here is argument of z, I'm going to call this gamma, as argument of z prime, and this thing is beta, which is argument of z double prime. And so what I am putting up is, here is an ideal tetrahedron, then it is the same as looking at similarity classes of Euclidean triangles, which is the same as looking at angles. So there are all of these three things are determining the same object. I think I put up this formula, and of course you can also go back. If you take a triangle and if you have alpha, gamma and beta, then you can go back also by writing z as sine of gamma divided by sine of beta, and e to the power I alpha. So then and it exactly goes back. So this is your z, and then this is your z prime, and so on. So it exactly goes back. So that was the picture. So what I want to just start off with is the volume of an ideal tetrahedron. And so we have the Lobachevsky function, is defined as an integral so you can plot this function and you get a maximum at pi over 3. You get this function, and this function has many properties. It is pi periodic, etc. So the main theorem is, if you have an ideal tetrahedron with angles like so you have delta is an ideal tetrahedron with dihedral angles alpha, beta, gamma, then the volume of delta is the Lobachevsky function at alpha plus Lobachevsky function at beta plus Lobachevsky function at gamma. Note that the dihedral angle over here, well, it's going to be the opposite angles are going to be the same, right? The dihedral angles. So all the linked triangles are similar because of the symmetry. So an example, you can do some multivariable calculus and maximize this function, some Lagrange multiplier, fundamental theorem, etc. And so there is an ideal tetrahedron of maximal volume when all of the angles are the same is pi over 3, and this is called the regular ideal tetrahedron. And the volume of this is going to be 3 times, this comes out to be 1.0149 something. This number is known as V, it's known as V tet for the maximum volume tetrahedron, but I am just going to be lazy and call it V3, but usually it is denoted as V tet. There is another example which is the regular ideal octahedron. So this is not a tetrahedron, but you can still compute its volume by dividing it into tetrahedra. So what is this? This is the so all dihedral angles are pi by 2. So in there are nice pictures on the web about of all of these things, especially in the Poincare ball model. You can see the symmetry, etc. And so what you can do is you can, if you have an octahedron like so, you can divide this by stellating this thing. You can put an edge from this vertex to this vertex and then divide it into 4 ideal tetrahedron. And then what is going to be the link over here, because everything is regular, this link here is actually a square, and now you are dividing the square. So each tetrahedron has angles pi by 2 and pi by 4. So that is what the triangle looks like. So now if you just do the computation for the Lobachevsky function and so on, you get this volume to be 8 times Lobachevsky function at pi by 4, and this is a number which is approximately, and this is also known as a V oct, which I am going to just write as V8. And just before we go to the next section, there are very interesting properties of the of Lobachevsky functions. But just before we go to the next section, notice that this formula for the volume is really in this, on this scale, you have the z's here and you have the angles here, right. So this is lying in the angle part of it. But then you can also do some very nice identities and realize this as something to do with a function directly of z. So I am just going to put that up. This is called the Bloch-Wigner dilogarithm. And so if you have the classical dilogarithm given by this series, then I do not know what date, but long back, Kammer realized a connection between the dilogarithm and Lobachevsky function. So he says that this is going to be so we are in that scheme out there. So, you have alpha minus and so the Bloch-Wigner dialogarithm is defined as d of z to be equal to imaginary of the dialogarithm, but and plus a correction term and this equals the volume of your ideal tetrahedron. It's the same, it's similar computation. The key point, the details of all of this are really in the fact that these functions can be defined not just by power series. If you define it as power series, you are only going to have some radius of convergence and so on. And so, the way to convert, you do analytic continuation, etc., and then all of these functions are written as an integral. And so, you can do this real analytic extensions and then make sure that they are defined on bigger space. So, this is I think real analytic on Z belonging to C minus 0 1, but not in the power series form. You need to do some, yes. Oh, yes, sir. Yes, thank you. Right. So, this will come up, the dialogarithm will come up later on when you see more about the volume conjecture, and I am not sure who is going to do it, but hopefully you will see how the volume conjecture is very related to this dialogarithm function, the motivation of it. All right. Any questions before? Yes.
Can I just make a quick comment?
Yes.
Kashayev's motivation for the Kashayev invariant was to quantize the dialogue. That was his whole. That was how the whole.
Okay, I am going to erase this picture that everyone, all of you have copied this down, and so I don't want to keep drawing this. Okay. All right. So, delta z is this ideal tetrahedron with edge parameter z and etc. Other edges z prime, z double prime. So, the next topic is the structure of hyperbolic 3 manifolds. So, your M is going to be a finite volume, complete, oriented hyperbolic 3 manifold. And so, the first part is rigidity. So, if you think about the geometric structures which we were discussing yesterday, if you think about just the torus, right, we just showed we saw the Euclidean structure on a torus by taking a square and then identifying opposite sides, but you could just very well take a rectangle and do that and you will get different area. And so, the area of the Euclidean torus is same as the area of this square or rectangle, and so clearly you have different geometric structures, they have different areas. So, you have same topology, but different geometry. Now, that does not happen in dimensions more than 3. So, what the rigidity theorem says is that if you have two hyperbolic n manifolds, for n greater than equal to 3, and if if f from m1 to m2 is a homotopy equivalence, then there exists an isometry H from M1 to M2 homotopic to F. This is just a very powerful theorem. It says that you cannot have different hyperbolic structures, and it has a lot of consequences for hyperbolic 3 manifolds and invariants. So it immediately gives you that topology implies geometry. So the first corollary of this is going to be if you have isomorphic pi 1s, implies M1 is isometric to M2. So the reason only the fundamental group is enough is because the universal cover of a hyperbolic 3 manifold or hyperbolic n manifold is Hn, and that is contractible. So these are k pi 1s. So k pi 1s are spaces whose fundamental groups are exactly the given group, and all other there are no other homotopy groups. And so what you can do is any isomorphism of groups then can be realized as is induced by a homotopy equivalence on the actual topological spaces, on the actual k pi 1s, because you can, once you have isomorphism of fundamental group, you can extend, you can take some one skeleton, or you can take some CW structure and then extend your map, which is inducing the isomorphism of pi 1 to the one skeleton, and then because there are no higher homotopy groups, you can keep extending, there are no obstructions to extending the map to bigger cells. And so that's the idea. So you can get this isomorphism by a homotopy equivalence, and then Master-Prasad rigidity implies that it's isometry, it's homotopic to isometry. And so this is very powerful. So your topology is giving you geometry. So topology is giving you geometry. And a second corollary then is, now you cannot have this situation where you for the Euclidean torus, you cannot have, if topology is the same, then you have to have the same area. So any geometric invariant is now a topological invariant. So that is like, that immediately gives you so many more, so many new invariants. So geometric invariants like volume, Cusp shapes, etc. are topological invariants. And the third corollary is something about a representation. So if you have a hyperbolic 3 manifold, for the I think you need oriented manifolds. Yeah. No, it's finite volume, complete oriented. Yeah. And so if you have so your M hyperbolic 3 manifold, you can see this as H3 modulo some Kleinian group. This is some discrete torsion free, etc. Discrete torsion free, and you can have more adjectives depending on, say, maybe co-finite volume, etc. And so what you are actually seeing is, this is the covering space action. This covering space action is actually by isometries, and so this gives you a representation from pi 1 of M, which is exactly what your covering space representation is. But now it's going to go into the isometries of H3, which is PSL to C, which is discrete. So the image here is discrete, and the representation is faithful, it's injective. So this is the discrete faithful representation, and it's denoted by rho naught, And what Mosto-Prasad rigidity is saying on the representation theory part is now this is determining the hyperbolic structure, because it's telling you how pi 1 acts as covering space transformations on H3, right. So if you have another structure, you may get some other discrete faithful representation. And so what this saying is that unique geometry means that any two discrete faithful representations are conjugate. So any two So this also has consequences for invariants. So this will give us, say, number theoretic invariants, like invariant, or I should say arithmetic invariants. So arithmetic invariants like trace fields and so on. So if we get time, maybe Kate may tell you about it, and or we can discuss in one of our discussion sessions, depending on how it goes. But so this gives us a very nice connection to number theory. So that's the first sort of rigidity. Why having hyperbolic geometry helps you study the topology of 3 manifolds and knots and links. The second is a structure theorem which tells us how you can work with hyperbolic 3 manifolds of this type, and what do they a priori look like, and why you can construct them using these ideal triangulations. So the next part is cusps. And so we'll assume M is non-compact hyperbolic 3 manifolds, and now there is a thick thin decomposition and plus Margulis lemma. I'm not going to tell you what these things are, but you can read up. Talking about further reading, I just uploaded the further reading list of some of the speakers who have sent me the list. So you can take a look. Sometimes there are links, sometimes there are names of articles which you can look up. So that should help you. So if you go to the schedule page, there is abstracts and then there is further reading. If you click on that, you will see the title of the talks and then the reading list. And so what this shows is the typical picture which you see for a hyperbolic 3 manifold drawn. You see something like a picture like this, and this is M, and what we are indicating is this is the thick part and this is the thin part. So this is the thin part and this is the thick part. And so what does the thin part look like? So the thin part is called a cusp. So the thin part, there are also a couple of other things for what the thin part of the manifold looks like, but if you kind of really make it very, very thin, then they will only look like cusp. So and these are the tori, and they are becoming smaller, and there's a metric description. So the thin part looks like T2 cross 0 infinity, and with the metric, the induced metric now is going to be so ds squared right at z and t. So this is becoming exponentially smaller, on this part, say on the z part, say on the z part plus say dt squared. So, this is as it is, except for this part gets really small. And what does the cusp actually look like? It's a quotient of z plus z. And what is it is a quotient of? So, this is called a cusp, and this is really a horoball which we saw yesterday and quotiented by z2 action by translations. So, how does that look? So, this looks like you have some horoball like this. So, everything above here, and now you are acting on this by translation. So, you have some fundamental domain like this, and that's the chimney which you see, which is being quotiented, and so this is being, so z2 actions by translations. So, z going to z plus a, z going to z plus b, where you have independent translations. So, that is what the cusp of a manifold looks like. And what is the consequence of this? A corollary of this this understanding the structure is that if you have a hyperbolic, a non-compact hyperbolic 3 manifold, then M is diffeomorphic to the interior of N, where N is a compact 3 manifold with boundary of N is some union of tori. See? So, it somehow just fits in that if you take knots and links, and if you take knots and link complements, so you take a regular neighborhood and then take out the interior of the regular neighborhood, then that's exactly can be hyperbolic, right, because it fits the topological description. You can have a manifold, a compact manifold with torus boundary. Pardon? That is the theorem. So, you require it to be a complete finite volume. Yeah, if you drop the finite volume, then you don't need torus boundary, and then there is the whole theory about how you can have any a compact manifold with any genus boundary. But then there is no rigidity either. So, now there is a whole space of hyperbolic structures, complete hyperbolic structures, and that is studied too. Thurston also studies that. Higher genus boundary and totally geodesic. You get rigidity? You do? Okay. I'm trying to think. I don't remember. Totally geodesic boundary. Oh, maybe yeah. Maybe it's hyperbolic. Yes. So now, as a consequence of Thurston's hyperbolization theorem for Haken manifolds, you can now get geometrization of knot complements. Of knot complements. So, let this be a knot.
These theorems tell you how many cusps are there?
Finitely many.
Yeah, but exact number can one find out?
Well, that's an invariant of the manifold, so it all depends. You can get manifolds with arbitrary number of cusps. They are more structured theorems. They are not really quantifying. Now they have, people have started working on really quantifying the Margulis constant and so on and how it relates. But that
If for
is,
not complement ring, is there a way to find out this also?
it's the number of link components is the number of cusps.
Oh, so then it's
Yeah, for a link complement is the number of cusps. It's the number of boundary components of n is the number of cusps. So for then either yes, but that may be harder to count. Yes. K is a torus. So either K is a torus knot, and then it's not hyperbolic. S3 minus K, among the geometries which we saw, it either has an has H2 cross E and SL2 tilde structure. So this is non-unique. Non-unique. The geometry. This is for non-compact. If you have closed manifolds, the geometry is unique. K is hyperbolic. What does it mean to say K is hyperbolic? Not, i.e., S3 minus K is a hyperbolic manifold. And in this case, this is unique geometry, unique geometry. In the last case, R, K is a satellite knot. And the satellite knot will have a non-trivial JHJ decomposition into the pieces of the type 1 or 2, and S3 minus K has non-trivial JSJ decomposition. If you have not seen torus knots or satellite knots, that's a good question for the discussion session. We can see that. What's that? It is. This is ciphered fibered with SL2 geometry, but it also has a surface bundle geometry. Satellite knot, no. That will contradict the JSJ decomposition, because the JSJ is saying that either you break into pieces which are either ciphered fibered or they are atoroidal. So the satellite has these tori which are exactly the JSJ tori. Yes. The JSJ decomposition is the decomposition along tori. So if you remember the statement from if you remember the statement of geometrization, you can break up, you can decompose your 3 manifold into S2 along S2s. That gives you the prime decomposition, but that is not enough to geometrize. You need to further decomposition along tori, and that is what is called JSJ decomposition. So now the next question is, how do you build hyperbolic 3 manifolds? So that's where we get ideal triangulations. That's my symbol for triangulation, and gluing equations. So let's look at one dimension lower. So if you look at a hyperbolic, say, punctured torus, gluing equations. So you have this thin part, and you have the cusp and everything, So, this is one dimension lower, this is T2 minus a point, and this has a hyperbolic structure. And what you can do is you can realize this hyperbolic structure by gluing two ideal triangles. In fact, there are infinitely many hyperbolic structures, and there are many ways you can do this. But so if you think about the Poincaré disk model, then you have this square, this ideal square, your points are at infinity, and you exactly glue them like you would glue your torus. And if you divide this into two ideal triangles, so you can see that your ideal triangles are actually gluing up to give you a punctured torus. So that is the idea which we are going to do for one dimension higher. Now already notice that you have to be very careful how you glue. You are of course gluing with isometries. So this is again coming back to the discussion we had last evening, is that in order to, so this is a piece of the hyperbolic plane. So inside the geometry is fine. Now as you go along the edge, you want to make sure that the geometry is preserved, so you glue them using isometries. But that is not enough, because that's just one co-dimension 1 face, but you also need to go to the co-dimension 2 face, which is the vertex. So you need to also make sure that around the vertices things glue up properly, so that you actually get a disk. And that is equivalent to saying that if you glue up using the isometries, you need to get a circle which actually is, so you need to make sure when you glue up, whichever isometries you are using to glue up, this circle is going to be part of the cusp right here. And the thick thin decomposition will tell you that this has to be a Euclidean circle. This is a Euclidean S1. Well, Euclidean S1 sounds a little fancy. It just means that it's R modulo Z with Z as translations. So we are going to exactly take this idea and now extend it to one dimension higher. All right. So let's just set up some notation. So we have M as before, and so I'm just going to draw M something like this. Right, so these are your tori. So you have your M is now we are just a compact oriented manifold. No geometry. We want to figure out how we can put a geometry on M, or how we can put a hyperbolic geometry on it. So right now we are only in topology, no geometry, only topology. Okay, so this is what we have is a compact oriented 3 manifold, and your boundary is some k equal to 1 to h of some tori. And now what we are going to do is we take M hat and we cone all the boundary components to points. So cone boundary of M to points. So like so, and now we are looking at tau be a triangulation of M hat, actually a delta complex structure, slightly stronger. So delta complex structure is does everyone know what a delta complex is? Right, you take simplices, you glue along faces, but you have oriented simplices. So when you glue along faces, you need to make sure the induced orientation on face has to match up. Right, so that's your delta complex structure. So you have so let tau be a delta complex such that you need one more condition, is that all the vertices of the delta complex have to be the cone points. So, such that vertices of tau are cone points right off here. And such a triangulation, well, now if you delete the cone points, you will get back m minus the boundary. So, then you have this whole compact non-compact thing, you remove boundary and so on. So, what we are now getting is tau minus vertices. So, there you see the ideal vertices coming up, the vertices are not there, is equal to m hat minus vertices, which is equal to m minus the boundary. And so, such a triangulation is called an ideal triangulation. No, this is everything is topological right now, no geometry or combinatorial. So, what we are doing is we are just taking this thing and then we are just there, you can't tell anything now. Yeah, m hat is you have a manifold with torus boundary component, you are just coning it off.
So the total thing is now m hat.
The total thing is m hat. Now, I am taking the triangulation such that the vertices of the triangulation are these cone points. So, when I delete the vertices, I am left with m minus the boundary, because that's the whole idea of cusp and everything, right. Okay. So, now this is a quick proposition that if you take this, you have Ti is the number of I simplices of tau, then what we get is that the Euler characteristic of m is 0 and the number of edges is the number of tetrahedra. The number of edges of the triangulation is the same as the number of tetrahedra. And so, now how are we going to try to make this thing hyperbolic? We are going to take this topological tetrahedron, topological simplex, and since we have all this throwing away vertices and so on, we are going to just assume that it is actually a hyperbolic ideal tetrahedron with some parameter. So, we are going to just assume the delta, each delta is actually some hyperbolic ideal tetrahedron with parameter zi. So, this is your hyperbolic ideal tetrahedron, and understand obstructions to gluing. Obstructions to extending the geometry, extending hyperbolic structure after gluing. So, what are the obstructions which can come up? So, again as the same thing as before. So, first is we are going to glue along faces. Now, what is the faces of an ideal tetrahedron? They are ideal triangles. We saw yesterday that there is only one isometric class of ideal triangles. So, first is the codimension 2 faces. So, that is the faces. So, faces are ideal triangles, but there is only one isometric class. So, you can glue all of the ideal triangles together. So, there exists unique isometric class. So, implies can glue such that the geometry extends along faces. right? You glue them together, the geometry extends. What is the next dimensional face or lower dimensional face is your edges, right? And so now when you glue up along the edges, so here is an edge and now you are gluing up. So here is one tetrahedron, here is another tetrahedron, here is another tetrahedron. So it has to be, the picture gets a little tricky. So these are 4 tetrahedra gluing up, but now these are not just topological, it has geometry, it has a shape. So we are going to glue up together. Now let us put this edge at 0 infinity, one vertex at 0, one vertex at infinity, and then look from up. So what picture do we see from up? So from infinity, what do we see? Here is your edge, and now here is a tetrahedron, here is another tetrahedron, here is another tetrahedron, they are all gluing up. Now if they go on gluing up, say something like this, right, they all have shapes, mind you. If they glue up something like this, that's no good, the geometry, there's a problem here. If they glue up say something like this, that's also no good. If they actually wind around several times, that also does not work. So it has to, when you glue up, it has to glue back up perfectly, it has to match perfectly. Do you see the idea? So the moment you get geometry, you have shapes now, you don't just have a topological thing. You could have the valency of the edge like 100, and you could have once you put the shapes in, these things can just go around and around and around, some shapes Zi, and then that won't work. It has to exactly fit in, then the geometry will extend around the edges. So there is a so now we have complex numbers, you can think of them as variables, and that gives you a condition, an obstruction, which is in form of a equation. So how does it work out? So first tetrahedron, let us arrange it as 0 1 Z1 for example. Now remember, multiplying by Z1, right, takes this face to this face. This is what the whole edge parameter does. So now when you take the second tetrahedron, instead of starting at 0 1, you just multiply it by Z2, then this is going to be 0. Well, let us multiply, use the isometry multiplication by Z1. So you are going to have, instead of this guy, you are going to have 0 Z1, and then this vertex is going to be Z1 Z2. Now you take the isometry multiplication by Z1 Z2 and then multiply by the third guy, and so then you will end up here as Z1 Z2 Z3. You see that? This is exactly what the edge parameter is doing. As you go along, the last thing has to be equal to 1. So that gives you an equation. So you have so this gives an equation for each edge. These are called the edge gluing equations. So what we have is, we have these delta Z1 up to delta Zn, these are your n ideal tetrahedra, and now you have edges. For every edge you get this. Remember, the number of edges is the same as the number of tetrahedra, and so what is the equation you get? Now I have written here Z1, Z2 and so on just for convenience, but this edge may be Z1 prime, Z2 prime depending, right? You are choosing that picture of the tetrahedron with Z and Z's and so on. So you are ordering everything. Now when you glue up, you could have Z primes, Z double primes, anything. So you have, so Zi, Aij, Zi prime, Aij prime, Zi double prime, Aij double prime equal to 1. There has to be a plus or minus because of a branch of a log and so on, but let us not get into that. You can determine the sign, it need not be always 1, it can be minus 1 also. So that is the edge gluing equations. There are n of these equations. So if they satisfy, if your parameters z1 to zn satisfy these equations, then you can extend the hyperbolic structure over the edge. So, are we done? Yeah, these are some numbers which are determined by the combinatorics of the triangulation. You have an ideal triangulation that will determine what the powers are. For every edge you have one equation, yeah. For j is the edges, oh sorry, yeah. So you have edges E1 up to En. So that is indexed by j. So for every edge you have this equation. So are we done now? Can we we'll say okay, you have n equations, you have n unknowns, we should get a 0-dimensional solution, we are all happy, that's it. There is one more dimensional face, right? The codimension 3 faces, which is the vertex. It's exactly the same thing we had before. So we also need to look at what happens at vertices. So we need to glue up together at vertices properly. So what happens at vertices? So your M complete, your completeness gives you that your cusp cross section has to be Euclidean torus, is a Euclidean torus. And okay, so here is the part which gets a little trickier. Now when you think of an ideal tetrahedron, if you look at, if you cut it by some horosphere which are horizontal planes, you are cutting out Euclidean triangles, but there is a scaling. The Euclidean triangles can be scaled, so they are only well defined with similarity. Now when you glue up together, you see these triangles are getting glued up, but when I look from the top, I do not know what height you are at, right. So what can happen is, this one glues up like this, but the next one glues up at a different height, the next one glues up at a different height, and so on. So what you need to make sure is, you need all the triangles, not only do they glue up via similarities, they actually glue up via Euclidean isometries. So at the same, well, that will happen if you can always cut this at the same height, but it is a little tricky because you have many cusps, you have many vertices, and you have many edges. So you could have some cut like this over here, something at a different vertex, something at a different vertex, and so on. So you need to make sure that all of those cross sections can be put up in some at a common height. So for example, if you take that cusp say at infinity, but and you can see all tetrahedra and you develop the map and so on, you should be able to cut and get it at the same level. That gives you another obstruction. So the way this is written up, if I don't have time to explain this in detail, but let me just write out something which will give you some intuition of what is going on. So you have your similarity of linked triangles, right, of a tetrahedra, right. All that means is these triangles I am talking about, they are at different height, right. What this gives is, you are gluing together, if you glue triangles together via isometry, you are able to extend geometry. If you glue them via similarity, you get a similarity structure. So this gives you a similarity structure on this cusp torus, and the completeness equation is the equation saying that this similarity structure has to be Euclidean. So the completeness equation is so the completeness equation is that the similarity structure at every cusp is Euclidean. Now the way that is done, the way this is done is, you pick a meridian and longitudinal basis for every cusp torus, and for every meridian and every longitude you get an equation which is encoding the dilation, right. What is the difference between similarities and isometries? Isometries are similarities with dilation factor 1. So you can catch that dilation factor, which is called in what is called the holonomy representation. This gives you some kind of a holonomy, and you can catch this dilation factor, and the way you catch it is exactly a very similar equation. So very similar equation. So you get an equation for meridian and longitude for each cusp. So you have n equations here. These are n equations. Now you get 2 for every cusp, so you get 2h equations. The equations are of exactly the same form. So equation same form as edge gluing equations. But they have different, of course they are going to have different exponents. That is just the angle equation, but these are stronger. And so the theorem is, now we have so we have these equations and so on, and these abstractions. So we say that if you can find a solution to these equations, we will get a hyperbolic structure. So that is the theorem. So let tau be an ideal triangulation of M with n tetrahedron and h cusps if a point, if say z1 naught dot zn naught with imaginary of zi not positive for all I, if this satisfies the gluing equations, which is edge and completeness, then M admits a hyperbolic structure. Yeah, by a hyperbolic structure we are always looking at complete. So could I go over for some time, maybe just like 5 minutes, because I started a little late. So all right, I just need to show you this example before the next series of talks start. You should see this example. So there's a very nice proposition. So it looks a little scary to compute all of these equations and satisfy and so on. Notice that if you have all the triangles, linked triangles, they are all equilateral, right? Then all the edges are the same. Then there is no option. If they glue up, they have to glue up using a Euclidean isometry. So if you are able to find a solution where all your angles are pi by 3, meaning that they are all regular ideal tetrahedra, then it has to be complete, because you are now gluing up equilateral triangles, and as you develop, you cannot, all the edges are the same length. So every time the similarity, the dilation factor is always 1, right. So the proposition says that you have a, if your ideal triangulation has all 8 edges of valence 6. What does that mean? It means that there are 6 tetrahedra, every edge is incident to 6 tetrahedra, right. So if you have pi by 3 times 6 is 2 pi. So that is why you need 6. And so then the point e to the power pi I by 3, that's exactly the z for the regular ideal tetrahedron, gives complete hyperbolic structure. So, in this case z equal to z prime equal to z double prime, everything is I pi by 3, and your tetrahedra, all tetrahedra are regular. Yeah. Well, does this ever happen? Right, you are like, this is too good. Well, you see the first example, and it happens on the first example. So, we can safely assume that this is true for all knots. That was a joke. Okay, so the way this happens is, as Elias said some time back, the knot theory is a theory of two knots, trefoil before for non-geometric and figure 8 for the geometric. So, that is the figure 8. So, here is the figure 8 knot, and now I am going to look at a triangulation of this, which I will show you next tomorrow in detail how to get this triangulation. But for now, think of this edge and think of this edge. I will just explain how this comes about. Okay, so you look at this knot, you want to look at the complement of the knot. So, the knot is actually not here. Okay, so, this edge here, you can see this edge is actually extending out to over here. This edge goes here. You see this, you can just push this edge and you can see this edge going over here, and or this edge you can see this edge going over here. You all see that, how you can just push this edge, right? There is you have a crossing and there is an edge between the crossing, you can just move the edge around, right? So, you just move the edge here, you can move the edge over here, you see that. So, all 4 of these are the same edge. Now, you can see faces, because what is on the board here are faces, right. So, here is one face, there is a triangular face, 1 edge, 2 edge, 3 edge. Notice that the knot is going off to infinity. So, you shrink the knot, right. So, the knot is really not there. So, here is a face, here is a face, here is a face. This is a bigone, and bigons are not geometric. So, you could they can vanish exactly this spanning this edge, it will vanish the bigone, and there is a face outside 1 2 3, see that. So, now you have 4 faces. So, you are building up, right. You are looking at the ideal point, which is the knot itself, you are looking at the edges, now you are looking at the faces, and now here are the 3 cells. If you think of the board as the plane, here is one 3 cell on this side and there is another 3 cell on the other side. One has to be careful about the gluing, they do not glue like we think they glue. If you try that, you will get back S3. But you have a so you have a 3 cell with 4 faces on it, right. It is 4 triangles on it, it is a tetrahedron. So, you have one tetrahedron on this side, you have one tetrahedron on the other side, and they glue up. And so, how do they glue up? You can see what is the valency of the blue edge. There is, here is 1, here is 2, right, here is 3, here is 4, and there should be 2 more on the other side. Is that, did I mess that up? I think, oh yeah, here is 5 and here is 6. You see that? 6 instances. You do not ignore the bygones. So, these get ignored. Ignore bygones, and now you can see that the faces, the blue edge, right, 1 2 3 4 5 6, and the red edge 1 2 3 4 5 6. Did I count that correct? I am just, anyway, you can count it, they are both 6 valent. And so, here is a 6 valent triangulation, and what we get is we can write down the edge gluing equations. You have to do some more work, and the edge gluing looks something like this. and for the second edge it looks like and so the solution is you can see this is a solution to this because everything is the same and there are 6 valence. If you just right, this is a sixth root of unity. And so what you can get once you have this solution to the gluing equations and so on is a very important invariant you can compute. You can compute the volume, right. So once you have a ideal triangulation, the volume of a manifold is just the Bloch-Wigner dialogarithm which we used before. You just get the volume. So here is figure 8 naught. So you have volume of S3 minus the figure 8 naught. This is the naught 4 1. It's affectionately called figure 8 naught, but its official name is 4 1, and that's going to be equal to 2 times e to the power pi I by 3, and this is exactly 2 times V3. So tomorrow we will see how to get this triangulation to write down these equations. So tomorrow we will see how to triangulate knot complements, and then we will do lots more examples coming from different kind of decompositions, polyhedral decompositions, right angle decompositions and so on, depending on the time. And tomorrow I think in the instead of a discussion we also have a computation session, right. So we will look at that all of this can be implemented on the computer, and there is a program which is called Snappy. So it takes some combinatorial data. This is based on the program Snappy. Snappy just it's peas with the shell. This is rare in the US. We buy peas only in the supermarket in the frozen aisle. Sometimes we can get them. We don't have to shell. So that's what Snappy. It was written by Jeff Weeks. He called it Snappy because I think he was growing snappies in his garden. That's why he called it Snappy. Anyway, so the other PY is another implementation by Nathan Dunfield and Mark Culler using Python, and so you can download it. If you Google Snappy, put in some math words like hyperbolic or something, because I think there are many companies called Snappy. So you get many non-math results. All right, let me stop here.
There's some URL. I have a link where one can install it from.
Yeah, there is. You just go to the website and install it. It's very straightforward. It's implemented.
It's in Sage. If you do the Sage Cloud, it's in the Sage Cloud if you don't want to install it.
So
You still need to run it on the computer. No, you don't need any Sage. You just go to the website. There is, if you are using Windows, click install. If you are using Linux, click install. Mac, click install. It's very fast. You don't need any computer expertise to install it.
Okay, so we have tea and snacks outside.
Oh, it's still not lunchtime. I was rushing because I thought it was lunchtime.
One more lecture.
We have some hats and stuff in the back as well. Can you explain this again? The